Hey, AP Chemsters, this is Mrs. Vanderwey bringing you Blankwalle, Chapter 12, Part 4. This is Solution, Equilibrium, and Factors Affecting Solubility. So what is solution equilibrium? It's when the rate of dissolving or dissolution, same thing, equals the rate of recrystallization. And folks, this is when you're talking about having really a liquid solvent and a solid solute, okay? We have seen equilibrium already in Chapter 11 when we talked about having the gases becoming vapor at the same rate as those gases recondensing back to the liquid. So the liquid's becoming the vapor, your rate of vaporization is equal to your rate of condensation. So again, we're going to hit equilibrium a whole lot more in Chapter 14, but whenever you think of equilibrium, you think of rates are being the same, okay? So let's look at this right over here, solution equilibrium. When we first put a chunk of sodium chloride in the beaker of water, okay, when it's first added, yes, sodium chloride, it begins to dissolve in water. And what does that mean? Can you continue to have more and more sodium chloride to be dissolved? The answer is yes. So at that point, if you can continue to dissolve more sodium chloride, it's considered to be unsaturated, okay? But then what happens? As time proceeds, okay, the solution becomes more concentrated. Some of the sodium and chloride ions can begin to recrystallize into the solid sodium chloride. And until that point, when you dissolve enough sodium chloride that you have more and more of that sodium chloride coming together to become that solute again. So it says when the rate of dissolution or dissolving equals the rate of recrystallization, dynamic equilibrium has been reached. So notice something. Until dynamic equilibrium has been reached, we have a single arrow. But when we hit equilibrium, notice what we have right here. We have a double arrow. So at this point, when you have dissolved the maximum amount of solute, all right, that's considered what? That is considered to be a saturated solution, okay? So when you have these constant concentration of ions in solution, no more can be dissolved, okay? That's considered saturated, okay? Then we have another phenomena called a supersaturated solution. This doesn't happen very often, but it can. And this is when more than the maximum amount of solute can be dissolved. You usually do this by heating up a solution, and then you keep adding more and more until it holds as much as it can at that hot solution. Then you let it slowly cool without disturbing it, and you're going to still now have the maximum amount. Let me show you what I'm talking about. Let's go back. Take that back. Let's not go back, all right? So I'll show you what I'm talking about when we get to the graph below, okay? Now, usually this supersaturated solution is when we think of fudge or rock candy. I don't know if you've ever made either, but what you do is you take a saucepan, you put some water in it, and you put some sugar in, a lot of sugar, an obscene amount of sugar in it, and you heat it up. All right, until it all dissolves. And then you put this, let's say it's rock candy, you put this in a glass jar or something, and if you just let it cool and sit, nothing will happen. But if you put in a string or something, maybe even like a wooden stick, like a popsicle stick in there, what has happened is that you have created what's called a site of nucleation. And when you put that foreign surface in the supersaturated solution, then it will crystallize out on that foreign surface, all right, that site of nucleation. And that's how you can make rock candy. Now with fudge, it's a little bit different, same principle. You heat up that obscene amount of fudge and you cool it down. But when you make really yummy, yummy fudge, it's not crunchy, is it? It's not like the sugar crystals have recrystallized. It's yummy and creamy. All right, it has not reformed the sugar. All right, but if you don't heat it up, all that sugar will not, won't dissolve, and then it's kind of gross. Okay, so I'll just put it that way. Supersaturated solutions. Maybe we can do that some point and have a little fun. We'll find out. All right, so let's do this. So what can change the solution equilibrium? I've already alluded to the first one, and that's you can change your temperature. And what about the other one? Evaporation of solvent. So remember that rock candy I was telling you about? If you let that jar just sit out, okay, and you don't put a string or a popsicle stick in it, but you don't put a lid on it, and some of that solvent is allowed to evaporate, it will crystallize out at that point, okay? But if you do put a lid on it and you don't allow your solvent to evaporate, it will stay very thick and gooey for a very long time, okay? All right, so let's talk about this temperature, okay, right here. So here's a graph, and let's check out this graph. What do you notice? Most of the salts are all ionic on here. As temperature goes up, so does solubility. We have one exception, that's sodium sulfate. But when I was telling you more about that supersaturated solution, let's use potassium chlorate because it's the easiest one to look at. So let's say at 30 degrees, you can only put 10 grams of potassium chlorate and it will be saturated. So these lines right here represent saturated solutions, okay? So this is the maximum amount that the solvent can hold at a given temperature. So right here, let's say you put 10 grams of potassium chlorate in here and it's saturated. But what if you heat it up? Hey, if you heat it up to 70 degrees, you can put 30 grams in. You can put more potassium chlorate than you could before. So what if you slowly, without disturbing it, cool it? Then it will still remain in solution and it will not precipitate out. But what if you stick a popsicle stick in it? How much will then precipitate out? Well, 30 minus 10, you're going to have 20 grams on that popsicle stick as solid potassium chlorate. All right, the other 10 grams will remain in solution. Okay, so that's what my reference to the supersaturated solution was. Okay, so it says in solids, increases in temperature always cause dissolving to occur more rapidly. That is a kinetics thing. Okay, you're going to dissolve quickly. You're going to dissolve a certain amount, but more quickly. Why is that? Because your liquid molecules are going faster, easier to separate. All right, therefore, increases in temperature usually increases solubility. Okay, why is that? Well, for the majority, all but your sodium sulfate, all right, many factors are involved. So I'm looking at calcium chloride. Look at this. Remember that was our hand warmer winner? What would make the best hand warmer? Well, why was that? Because the enthalpy was one of the greatest, okay? Remember that? Sodium chloride's enthalpy wasn't so great, was it? All right, so it only goes up by a little bit. Isn't that what your graph looked like for your hand warmer lab too? Interesting, okay? So enthalpy is definitely a factor involved. What about entropy? Are we increasing the entropy of the solute molecules? Yes, we go from, let's say, one formula unit of potassium chloride or potassium chlorate, and when it dissolves, you get 2 ions. With calcium chloride, when you have one formula unit of calcium chloride dissolved, you get 3 ions. So that's more entropy. But what else is happening, though? You got to think about water. Okay, so you have 2 things going. When you increase the temperature, your water molecules are going faster. So in that respect, entropy is increasing. But some of those liquid molecules are now organizing themselves around those ions. So in that sense, entropy is decreasing. So it's not a clear-cut winner in a sense of what wins out, the entropy that they're going faster or the entropy of the organization of the water molecules surrounding those ions, okay? What else is involved? Temperature. So if I have enthalpy, entropy, and temperature, then Gibbs free energy can also predict whether these are increases in temperature will increase solubility, or in the case of sodium sulfate, will decrease the solubility. So something to think about. All right, let's go on to the next page. All right. Well, up until now, we've been talking about solutions of solids dissolving in liquids. Are solids the only thing that can dissolve in a liquid? The answer is no. Gases can too. And I bet our fish population is really happy for that as well, okay? So temperature can affect the solubility of gases in water. As I wrote here, problem number 7, observe a glass of hot water, explain your observations. If you can, I would really, really love it if you were to pause the video, go to your kitchen, pull out a clear glass, and get your water really, really hot, put some of that hot water in the glass and make an observation, all right? So if you can, if you're a car, I don't think you can do this, but if you're at home, please do this, all right? And come back when you're done. Well, I hope you did it. Now, this picture here actually came from my kitchen. All right, these are my glasses. They're actually my glasses. All right, this is the cold water and this is the warm water. I don't know if you can really tell a difference. That's why I wanted you to go and do it yourself. But my right-hand glass, my hot water, is actually a little bit cloudier than this one. Can you see the difference? If you're looking closely, you might notice this looks cloudier than this, okay? Why is it so cloudy? What do you think makes the cloudiness? Well, what's making it are the gas bubbles, all right? I have a quick story to tell you, and then we got to go on, all right? So when I was in elementary school, I'll never forget this, because I got yelled at, and I never got yelled at. We had, I don't know, pet something, pet turtle, or maybe it was even pet fish. I don't remember. But every week, a different kid had to clean out this pet's cage, all right, or the glass bowl in the aquarium. So one week it was my turn. And so I went to do it, and it took me a really, really long time to do it. And the reason being, when I used the hot water, I thought the water was dirty. So I kept dumping it out, thinking I'm really doing a good job cleaning it because the water looked dirty. And I put more hot water in, I scrub away, and it still looked dirty. And I dumped it out, and I put more hot water in, thinking it was dirty. It really wasn't dirty. It was hot. All right. Then my teacher yelled at me for taking so long. Just put the water in. I said, but it's dirty. No, it isn't. Put the water in. And so I learned quite a lesson. All right. So anyway, your hot water is cloudy. Why? Because of the gas bubbles that are coming out of solution. All right. So let's check this out. So look at this graph over here. What is the relationship between temperature and solubility of gases? There is no exception to this, unlike your ionics, right? Every single one, as temperature goes up, solubility goes down, all right? That's your relationship. It's an inverse relationship, okay? So what are some examples of this, all right? How about goldfish versus tropical fish? If you had goldfish, do you have to have a heat warmer in there? The answer is no, okay? Goldfish live in cold water. But if you have some kind of a tropical fish tank, don't you need a heater in it? Yes, you do. Why is that? It's because here's the oxygen. Tropical fish don't need nearly as much oxygen as goldfish do. All right. And if you put tropical fish in cold water, you're going to give them something called the bends. There's just too much gas in there and they will die. All right. So what's another one? Well, how about the cold pop versus warm pop? So the cold pop, all right, or in this case, cold water is your clear, your hot water is cloudy. Same thing here. If you ever tried to pour a can of cold pop, all right, not a whole lot of bubbles involved. If you pour out a can of warm pop, lots of bubbles. Oh, I have another story about that too. I'll tell you about that later. All right, and then once again, here, let me move these over. All right, whoops. What makes your hot water cloudy? And I wrote, look closely. There are gas bubbles coming out of solution making it look cloudy. So go ahead and read problem number 8 and decide what's going on. Okay, so pause this and see what you get. All right, welcome back. Well, let's see here. As a solution is cooled, all right, to room temperature, all right, what's happening when the solution is cooled? All right, that means temperature is getting colder. So what does that mean? More and more nitrogen stays in solution. All right, so do some nitrogen gas bubbles out of solution? No. All right, because you're cooling it down, so there's fewer gas molecules coming out of solution. More of them are dissolved. Does some potassium bromide precipitate out of the solution? Well, what happens when you have a cold thing, all right, you're not going to dissolve as much, all right? So that could be. Some nitrogen gas bubbles out of solution and some of it precipitates. Well, that's assuming A was right or nothing happens. I think it's answer B. All right, so the nitrogen gas is not, here's nitrogen, is not going to bubble out. It's going to, more and more is going to be redissolved into it. If you go back and look at the chart from the last section, you will see you can have less and less potassium bromide, so it could precipitate out. Okay, so this is a good place to stop. Don't wait to be great. We'll see you for part 2. Bye-bye.